For today's video, we will be looking at the simple Math Olympiad question from the 1999 Ukrainian Math Olympiad, which I'll be using to illustrate some principles from modulo arithmetic. The question asks, can the number 1999 be written in the form n power 4 plus m cubed minus m, where the m and n are integers. Questions of this form are often called Diophantine equations, a class of equations which admit integer solutions only. We would need to find all the m and n which satisfies the equation, or to prove that there isn't any of them. Before we solve the problem, here's a brief refresher or introduction to modulo arithmetic, if you haven't seen it yet. We say that A is congruent to B modulo M if A and B has the same remainder upon division by M. One good thing about this congruence notation is that we can essentially manipulate it like an equation. For example, we can move B to one side of an equation to get A minus B is congruent to 0 modulo M. Multiply both sides of the congruence with a constant integer, or even raise both A and B to the same power. You should try and verify that these are indeed true. Now we can go back to the question. It seems natural to factorize m cubed minus m, and doing so, we get the equation 1999 minus m power 4 equals m times m minus 1 times m plus 1. What does this all mean? It means that the right hand side of an equation is a product of three consecutive integers, and as we know, there must be a number which is divisible by 3 among these three of them. Taking Q of this, we can write 1999 minus m power 4 is congruent to 0 modulo 3. And since the number leaves a remainder of 2 upon division by 3, we further simplify to get m power 4 is congruent to 2 modulo 3. Is it possible then to find such an integer n whose fourth power leaves a remainder of 2 upon division by 3? To investigate, let's try the good old technique of divide and conquer. Any integer n we start out with would have left a remainder of 0, 1, or 2 upon division by 3. By separating into 3 different cases and raising n to the fourth power, we see that any fourth power of an integer can only be congruent to 0 or 1 modulo 3. This then proves that no such n which satisfy the congruence exists, and so there's no solution to our original equation, at least in integers. One quick note though, this method of congruence is useful when we intend to show that no solution exists. We are essentially proving a stronger version of a question by saying that there's no solution to a congruence, and by a lesser extension, there's no solution to the originally intended equation. This technique is very powerful if we are trying to prove non-existence of solutions, but less so if we are trying to find a solution. So use it sparingly with this in mind. We have come to the end of the video. I hope you have enjoyed it, and I will see you in the next one.